All right, I'm back to go over this time number 13 in this video. So let me open up my tablet and then we'll get started. All right, I'm back to go over number 13 in this video. And if you guys need something else, just you write me an email. So I'm gonna go ahead and this is a fun one. So I'll copy this to another page and then I'll go over number 13. Hold on. Where did you go? Copy this again. Okay, I'll make this a little bit bigger. All right. So if T of T, big T of little t, is equal to 58 times e to the negative 0.044t plus 72, it's asking what happens to t and t prime as little t increases. Okay, so as we go to the right side of this graph, what are these t and the derivative function doing? Now on your exam, you're allowed to use a graphing calculator, a handheld device, but just to show you a quick picture, I'm going to go ahead and graph this and just talk about it, but I'll show you how to do the math work to support it. So the equation that we're graphing is 58 e to the negative 0.044. Decimals don't like t, so I'm going to just go ahead and change the variable to x plus 72. All right, I want you to look at the graph here, okay? Where are you, graph? Oh, I see it. Now, as x increases, as t increases, what is the graph doing? It looked like it was decreasing for a second, right? It was going down, but do you guys see how it's leveling out? Like, it's not going to go down forever to negative infinity. It definitely has a horizontal asymptote. Where do you think that horizontal asymptote is? Look, this is an exponential function that's been shifted up 72 units up. So do you believe me if I tell you that this graph has a horizontal asymptote at y equals 72? So by the look of the graph, this is what I found out. As t or x increases, as the graph goes to the right side, as we go and plug in more bigger and bigger and bigger x value, what's happening to the function? The function is getting closer and closer and closer to 72. So I'm going to go ahead and show that using algebra or calculus. You can probably do some limit, okay? But what else? What else? They also wanted to talk about what t prime is doing. And t prime is the rate of change, right? The slope of a tangent line, okay? All right, this is a thing. It's going down. The graph itself is going down. You guys see that, right? But in the beginning, it was going down very, very rapidly, right? It was going down very rapidly. But you see how it's slowing down, right? It's kind of slowing down. So as t increase, we are seeing that the rate of change, how fast it is going down, is kind of slowing down, right? We can also find the derivative function and then graph it, okay? Just like how we figured out the original function is approaching 72. But I just wanted to show you a picture, and that's what we kind of want to explain using math, okay? So I'm going to go back, and let's do this together. So they really never said, like, increase to what, okay? I just feel like some of these problems that we are solving are very open-ended, and sometimes like we misinterpret it or misunderstand the direction. But when I see this problem that Nova Online typed up for us, this is what I'm thinking. What they mean by t increases, the little t increases, is what happens as little t goes to infinity. So this is what I'm gonna do first. I am going to find the limit as t goes to positive infinity of t of t. And the answer to this will tell me, it better come out to be 72, right? It better come out to be 72. So let me do that first, okay? So limit as t approaches positive infinity of 58 e to the negative 0.044t plus 72. I don't know, guys. I mean, you guys did limit back in unit 1. So I don't know, you always surprise me with your very creative problem solving, but this is how Sue sees it. So I'll take the limit of these two, okay? How can I simplify this? Because I can't plug in infinity right now, right? Okay. But you notice that this term right there has a negative exponent, right? That term right there has a negative exponent. So I can send it to the bottom of the fraction. Look at this. I can write this as 58 over e to the positive 0.044t, right? We're using that exponent property, plus 72. You know, we can separate that too, but I'll just put 72 here, okay? Now, you remember this one property? Back in, I can't remember the textbook section number, so I won't open up the textbook. But remember, the limit as x approaches, or in this case, t approaches either the positive or negative infinity of a quotient that is in the form of k over x to the nth power. Okay, that's equal to 0, right? You guys remember that, right? So what's happening is, and I think this is gonna be similar, as the bottom of the fraction gets really, really, really big. Okay, imagine you're dividing something by a large number. You're dividing something by a large number. What happened? Like, think about it, you have $2 or $58, and then you're dividing it to like infinite number of people. Like, each of them will get like what? $0, right? And that's happening. That's what's happening over here. I'm gonna circle this, okay? I'm gonna circle this in red. What I circled in red is going straight to 0, okay? Because imagine we are dividing 58 by an exponential term, e raised to an infinite power, okay? All right, hold on. If you don't believe me, I'm gonna go ahead and write this in a Desmo scientific calculator, just a calculator. Desmo scientific calculator. So what happened if you divide 58 by e to a large number, like let's say 10? You see it's getting to almost 0, right? What about 100? Now, if, at that point it's so small they have to bring out the exponential, what's it called, the scientific notation. But what if it's 11 was too big? So like already at 10, it's so small. It's like 0.000. So imagine putting infinity for the exponent. Like when I type in 1000, they already told me that's equal to 0. So I wanted to show you why that first part just becomes 0, okay? The first part just becomes 0. And there's nowhere to plug in the t here. So the only thing that survives this is just 72. So I don't know if this is the way that the original problem writer, like whoever designed this question, was seeing this, but this is how I see it. I know that if I graph this t of t, we have a horizontal asymptote at 72, because as little t increases, the function is getting closer and closer to 72. Okay, because the first part just becomes 0. And I guess you can write that part up in a little more organized way. You can actually evaluate the limit. But if I see that, I think I'll like it. If you can do this for me on the exam, I say, okay, the student knows what it means by t increases, because he's taking t to infinity. And that it comes out to be 72. And I may mention something like y equals 72 is the horizontal asymptote of t of t in graph, when graphed, or in the graph. But that's something that you can mention in your test, and I think that's pretty good. It talks about what the graph does as t gets really big. But now, what about the second part? Well, the second part. Now I need to talk about the t prime of t. So how about we first find the derivative function? So if the original function is this, because now I'm doing the second part, let's find the derivative of this function and approach this, do it the same method. So t prime of t, you're gonna have to remember how to take the derivative of this, and we'll multiply this 58 by negative 0.044, okay? Hold on. 58 times negative 0.044. That came out to be negative 2.552, and that's my new coefficient, right? All right, go back and write the original exponential term, e to the negative 0.044 t, and the derivative of 72, that will just be 0, so that's gone. So we have a new exponential function. You want to see the graph of this real quick just to get an idea of what it's doing as x gets really, really big, or t gets really, really big. So look, if I graph this function, the derivative function, I'll just say y equals, or I don't even need to, negative 2.552 e raised to the negative 0.044x, okay? If you look at the graph of this, where are you, the graph? You know what? Kind of unexpected, because I thought it was going to slow. No. That's okay. That's okay. That's okay. This is good. This is very good. Look, it started low. Okay, it started low. Okay, but we shouldn't really look at that part. We should look at how fast it's going up. It was going up. Oh, it was increasing. And then what's the graph doing? It's slowing down, right? And what is it approaching? What is it approaching? What would you say the horizontal asymptote of this graph is? See, as we keep on going to the right, the horizontal asymptote is actually at y equals 0, right? This red graph is getting infinitely close to that green dotted line of y equals 0. And it's because, look, this is an exponential function, okay, with no vertical shift. There is no +5 or -10 that shifted the graph up or down at all. And remember, by default, a basic exponential function, they always have a horizontal asymptote at y equals 0. So I know, by just graphing it real quick, what this graph will be doing as we go to the right side as t increases. It's going to approach 0. I saw that. So that's why I want that's what I want to include in my work. So let's see. We can find the limit. We can take the limit as little t goes to positive infinity of t prime of t. That is limit as little t approaches infinity of negative 552 e raised to the negative 0.044 t. And you know what I'm going to do? This guy right there has a negative exponent, so I'm going to make it into a fraction, okay? Limit as little t approaches positive infinity of negative 2.552 on top of the fraction, but the exponential term will go to the bottom and the exponent is now positive. Now look at that. If you were to plug in, this infinity here, what will happen to the denominator? The denominator will get super big, right? So what's this limit going to turn out to be? We're gonna be dividing negative 2.552 by a large number. So if I just type this in to show you what it looks like, we're doing negative 2.552 divided by e to the 0.044 times a very big number like 10 or 100 or 1,000, okay, or 99. You see what it's getting close to? It's getting close to, again, 0, right? It's gonna get close to 0. So when the bottom of the fraction gets infinitely big, okay, because That's what's going to happen when we raise e to an infinite power. We're dividing a quotient. We're dividing the numerator by a large number. And if you do that, that just becomes 0. So I can say that as little t increases, okay, here's my final answer, okay? As little t increases, t approaches 72, and t prime approaches 0, okay? Some students will be a little bit more ambiguous. Like they will say something like, as little t increases, t increase or decrease. You may be right, but if you just say that, then it sounds like it's going up without bound or going down without bound. That it's just going to go to infinity or positive or negative infinity. So I did want to be a little more specific. That's why I brought up all this limit, okay? I can't remember if this is, because, you know, I made up these similar problems by looking at the actual exam problems. So hopefully they are similar enough for you. But if you just simply say, oh, it increased or decreased, I may take some partial credit off. Because if you just simply say goes up, then I'm going to assume that it's going to go up forever, right? If you just say it goes down, then, and maybe they are going to do that. Maybe they will do that. So for example, you guys, if you get a function that looks like this, I'm just going to make something up. Like y equals, hold on, you take a look, 50 times e to the, like 0.05x. Let's say that's the function. Okay, let's say that's the function. But if you get that function, now does this function have a horizontal asymptote to the right side? Not really, right? So if you see something like that, then you may be able to just tell me, oh, it increases without bound. It just goes up to infinity. I think that's fine. But for an exponential decay function that I had in my examples, they weren't going up forever. They were going to a specific value of 72, okay? Also, so the reason for something like this will be, as t increases, big T of t will increase without bound, okay, will increase because there's no horizontal asymptote to the right end, right? I would find the derivative of this function and do the same thing, but maybe it will be okay because if they're not approaching any number, and if you just say they increase, for me that will be okay too. But for the decaying function, like if you are, I wouldn't say unlucky, if okay, if you run into these exponential decay function that's going down to a specific value, I would like for you to mention what those numbers are. But hey, if it's just an exponential growth function that's going up without bound, you can just say increases and that will be okay. I would love to see some reasoning. You may mention the graph and how the graph is going up without bound to the right side. That will be okay. The limit will just come out to be positive infinity, or does not exist. But I'm excited to read how you're going to explain your reasoning on number 13 on your exam 2 this week. Okay, so that's it for number 13. You send me something else now. Okay.